Okay, currents and also potentials and potential energy, mixing all of them together here. So think about this, that just imagine some wire, some piece of a circuit and current is flowing through it. Ordinarily, we treat plain old wire as having just about no resistance at all. Remember where resistance comes from. This is the result of the drag force on the charged particles as they try to flow through here, and they see lots of obstructions in their way, that the atoms and ions that are inside inside the metal, forces from those things makes the velocity of the charged particles keep on changing, so that overall they'll move, but it's a very zigzaggy motion and not as fast as it would be without that drag force. Ordinarily, wire made of good conducting material, for most purposes, we can say it's got just plain zero resistance. All the resistance is usually lumped into particular circuit elements at specific places in the circuit, and lots of different things can all be represented as a lump of resistance. But here's a couple of important points. Go back to the basic relation here between current and the potential difference that causes current and the resistance to that current. Rewrite the equation this way, right? Potential difference equals the current that flows between the 2 points that have that potential difference times the resistance between those 2 points. But for good conducting wire that has approximately zero resistance, well, if that term is zero, then potential difference is zero. In other words, for normal wire with just about zero resistance, there's just about zero potential difference between any 2 points in that wire. Or to put it another way, there's no potential difference between any 2 points in a normal wire, then all points are at the same potential. As the charged particles move from here to here, they don't see any change in potential. And of course, when there's no change in potential, we know there's no electric field. When there is some resistance and current flows through that resistance, that's always associated with a potential difference. So here, in this one circuit element where the resistance is not zero, there is a potential difference between here and here. There aren't any potential differences out here. In other words, you get potential differences only where you need them. The current needs a potential difference between the two ends of this circuit element in order to produce an electric field, and that electric field is needed so that there will be a force that keeps on pushing those charged particles forward. Without that force, all you have in here is the drag force pushing backwards and slowing the charged particles down to a stop. You get no current. Here, where there is very little resistance, in other words, very little drag force, there's no need for an electric force to keep on pushing things through. So there's no need for an electric field. So there's no need for any potential difference. Okay. Now let's think about this situation again, and we'll say that there's current moving left to right. That's the so-called conventional current. We imagine positive charges moving, then those imaginary positive charges are what constitute this sort of conventional current, even though in a normal metal, it's electrons negatively charged particles flowing the other way. But let's say that here, the potential right here is, we'll call it VH, and V low, V high and V low, so of course higher potential here, lower potential here, and where there's a potential difference there's an electric field, and the electric field always points from higher towards lower potential. So there's an electric field pointing that way, and the direction of electric field is the direction of the force that a positive charge would feel. So the positive charges that we're imagining make up this conventional current all feel a force that way. Force on a positive charge is that way. So that's the setup. And now let's imagine just one charged particle moving from here to here, moving all the way through this this piece of resistance here in the circuit. Velocity of that charged particle is left to right. And let's take this, everything that's here inside this lump of resistance and this charge here, we'll take that to be our system. And we'll say it's a pretty good approximation to say that it's an isolated system. There are no forces acting on this charge other than the force from the electric field and the drag force. And by this point, you know the drill. If it's an isolated system, there are no external forces that are doing work on the system. That's what isolated means. And so the total energy of the system cannot change. So the total energy of the system does not change, but of course, changes, or the net change in the whole total energy of the system could be made up of some kinetic energy changes and some potential energy changes. But of course, since this is zero, what else do we know? Well, we actually know that for normal electric current, this is zero also. How do we know that? Well, we know it because current is constant. You turn on a light bulb and it shines with a steady brightness. It doesn't dim, it doesn't get brighter, but the brightness doesn't oscillate. That's because the current through that light bulb is constant. Right? You attach a meter anywhere in at least in any circuit that gets its potential difference from batteries, and when you measure the current, you find that the current is constant, not growing, not shrinking, it's constant. So you'd get a constant current only if the velocity of the charged particles is constant. And if the velocity of the charged particles are constant, if the velocity of this thing is constant, then its kinetic energy does not change as it moves from here to here. But there is a potential energy change and so that means there has to be an equal and opposite change in some other kind of energy somewhere else in order to keep the net change zero. And that other change is going to, in this case, be in the thermal energy, the total kinetic plus potential energy of all the molecules that make up this, this circuit element. So let's think about this for a minute. That's just equal to the final minus initial electric potential energy. Well, potential energy is just charge times potential. There's the charge, and the final potential is the potential that the charge sees when it's here on the way out of the resistance, V low. And then initial was charge times the potential that the charge saw when it was here just entering that lump of resistance, V high. Or factor out that Q and you've got V low minus V high. This is just delta V, right, the final minus the initial potential, and you can see that it's negative. Because the initial potential was higher and the final potential was lower. So this is negative, and we're imagining a positive particle passing through that lump of resistance. Make sure, just note that. So that's a positive term times a negative factor. That means this thing is negative. Potential energy is lost from this system, but where does that potential energy go? Well, it must go there. It must go into an increase in the thermal energy of the system. And commonly in just say an ordinary lump of resistance, and that's basically say what the filament is in an old-fashioned light bulb, just a lump of resistance. That increased thermal energy means the temperature rises, and eventually the temperature rises enough that it starts glowing. That's basically just how it works in an old-fashioned light bulb. Or in general, what we can say is that whenever current passes through any circuit element that has some kind of resistance, some energy is left behind as the current passes through. Kinetic energy is not lost, but potential energy is lost every time one of these charged particles moves from a higher to a lower potential. And that energy then stays inside this circuit element. Sometimes that energy that stays behind just shows up as thermal energy. The thing has a higher temperature, gets hotter, or the energy that stays behind is used to do something useful. When you plug in a refrigerator or a TV or a computer, essentially the same thing is happening as happened here. Current passes through, and as it passes through, some energy is left behind after the current has passed through. And then that energy is used to run the refrigerator or run the TV, or that energy is used to run the computer. In other words, we can think of anything that needs electric current in order to operate, needs electric current because it's going to take energy from that electric current and use that energy to operate. We can think of anything that takes energy from an electric current as essentially just a lump of resistance. And often we want to know how fast that thing is taking energy from the current. How many joules per second of energy are being taken from the current and kept here in this lump of resistance. Rate at which energy is received or energy is taken. We've seen that before with waves. That's called power. Power is just the energy received in a certain amount of time. Well, in this case, in this simple example, the energy received was this energy, and it came from here. So this is actually a negative number, so the amount of energy received, taken by this lump of resistance, is just the absolute value of this, which is just Q times the absolute value of the potential difference between the two ends of this resistance. But now think about that term right there, Q divided by delta T. What is delta T really? Delta T is the amount of time Q spends inside this resistance. Or to put it another way, it's the amount of time it takes the charge to move from here to here. So if you're standing here and counting how much charge per second passes by this point, and you start watching when the charge is right here, it'll take delta T seconds for you to see this charge pass by. And we're imagining this is the only one that passes by in that time. Right? We're thinking about just one charge passing through and no other charges. So really, this is coulombs divided by the amount of time it took to see that many coulombs of charge pass by. Coulombs per second passing by some point in a circuit, that's current. So power, we could calculate as current times the magnitude of the potential difference between the two ends of the thing that's having that current pass through and receiving that much power. Now there are two other ways that we could write a power equation that are useful in different circumstances, and those other ways simply come from applying Ohm's law. If we take this way of writing current, potential difference over resistance, and put that expression, potential difference over resistance, here, then we have a second way of writing power. Power is also potential difference over R times potential difference, or potential difference squared over R. And there's a second equation. And then a third equation, you can rewrite this as just potential difference equals I times R, and then take this way of writing potential difference, current times resistance, and put that in this slot. So you've got current times resistance. Our power is current squared times resistance. So we've got these three different rules, and you have to be careful how you use them. They're relevant in different situations. Superficially, you might think, say comparing these two, you might think, this rule says power is proportional to resistance, and it looks like this rule says power is inversely proportional to resistance. Well, that's true sometimes. Obviously, you can't have power proportional to the resistance and simultaneously inversely proportional to the resistance. But there will be some situations where power is proportional to resistance, and there'll be different situations where power is inversely proportional to resistance. Let's look at an example of that. First, just imagine two lumps of resistance in a row in the same path. Resistance 1, resistance 2, and we'll say resistance 1 is a bigger resistance, and there's current flowing through. Go back to that principle of conservation of current. Everywhere in the current's path, as long as the current doesn't branch out into two or more paths, anywhere in that current's path, the current is the same as it is anywhere else, regardless of differences. Obviously, the path looks different here than it does here, but as far as current is concerned, you've got the same current here as you do here. Same number of coulombs per second passing through this one as are passing through this one. So current through the first resistor is just the same as current through the second resistor. So in other words, if you take that fact and then look at this, then in this case, this is a constant. It's the same for both resistors, and the only variables are power and resistance. So in this case, power is proportional to resistance, which means the bigger resistor has the bigger power. By the way, important piece of terminology here. This is called resistors in series, or circuit elements in series. Series just means one after the other in the same path, or another way of saying it, series means the same current. If two things are in series, if two circuit elements are in series, they have the same current passing through them. Series means same current. Now let's take a look at a different situation where we'll again compare the power received by two different resistors. But now imagine that those two different resistors are, let's say, light bulbs, lamps both connected to the same wall socket. Since they're both connected to the same wall socket, they're getting the same potential difference. Right? The potential difference is supplied by the wall socket. So we would show that kind of a situation like this. Here's our normal symbol for a potential difference, where in this circuit these 2 points are at different potentials. The longer line always represents the higher potential. The shorter line represents the lower potential. And then here's one of those light bulbs represented by a resistance, because that's basically what a light bulb does. It does the same thing as a lump of resistance. Current passes through, and then that light bulb, just like a resistor, pulls energy off of that current and holds on to some of that energy and uses it either to heat up the resistor or uses it to power some kind of device. And then the other one is connected like this. And again, we'll say R1 is bigger than R2. Now, in this case, they'll have these two resistors will have different currents, but they share the same potential difference. How does this picture show that? Well, call the potential right here just high potential, right? The potential at the high pole of the battery, and then V low, low potential. And then remember our wire approximation. Whenever we have just plain wire and we can say that wire has essentially no resistance, then every point in that wire is at the same potential. Or to put it another way, any points connected by the same wire with nothing else in between are at the same potential. So this point is connected to this point by nothing but wire, so they're at the same potential. And this point is connected to this point by nothing but wire. So those are at the same potential. And likewise, this point is connected to this point by nothing but wire, so they're at the same potential, both V low. And this point is connected to this point by nothing but wire, so they are also at the same potential. In other words, the potential difference between the two ends of resistor 1 is V high minus V low, and the potential difference between the two ends of resistor 2 is V high minus V low. The potential difference between the two ends of R1 is then just the same as the potential difference between the two ends of R2. V high minus V low for both of them. So in that case, we have that. So same voltage, but different resistances. Of course, go back to Ohm's law, and that tells you you're going to get different currents in this case. But there's something else that the two circuit elements have in common. Not current, but potential difference. Not current this time, but potential difference this time. And another piece of terminology, we call this kind of an arrangement parallel, where parallel means sharing the same potential difference. Series means they share the same current, parallel means they share the same potential difference, and they share the same potential difference because corresponding sides of each of these circuit elements are connected by nothing but wire. This point and this point are connected by nothing but wire, so they must have the same potential difference. This point and this point are connected by nothing but wire, so they must have the same potential difference, or they must have the same potential. These points connected by nothing but wire must have the same potential. So this potential difference is the same as this potential difference. Okay, now look at one of those equations that had delta V in it. Power is potential difference squared over resistance. Now, in the parallel case, this is a constant. This is the same for both resistances. So you have a power equal to some constant over a variable resistance, which means power and resistance are inversely proportional. When two things are inversely proportional, if this thing gets larger, that means this thing gets smaller. If this thing is smaller, then this thing is larger. So the smaller resistance will get the larger power in this case. R2 gets the larger power. So that's the basics of how power works. And then you'll have a few exercises on thinking about power in the next few assignments, so you can try them now.